Assalamualaikum and good day. This video is about the sensitivity analysis when changing the right-hand side of an LP problem. It is often important for a company to determine how a change in a constraint's right-hand side changes the LP's optimal Z value. With this in mind, recognizing the dual price and their feasibility ranges are rooted in making changes in the right-hand side of the constraint. The dual price, or also known as shadow price, for the ith constraint of LP is the amount by which the optimal Z value is improved. Improvement means increase in the maximum problem and decrease in the minimum problem if the right-hand side of the ith constraint is increased or decreased by 1 unit. Let's refer to the Tycho original model. This is the original Tycho problem. Suppose that D1, D2 and D3 are the positive or negative changes made in the allotted daily manufacturing time of operations A, B and C respectively. Thus, the Tycho model can be changed to V plus D1 to the right-hand side of the first constraint, D2 to the right-hand side of the second constraint, and D3 to the right-hand side of the constraint. To express the optimum simplex tableau of the modified problem in terms of the changes D1, D2, and D3, we first rewrite the starting tableau using the new right-hand side. Okay, before we make the changes to the right-hand side of operation A, B, and C, the initial tableau of the Tycho problem is this. Okay, we take the original model. Okay, we have maximized Z and we transfer all these variables to the left-hand side. So we get Z minus 3x1 minus 2x2 minus 5x3 equals to 0. The coefficient of all select variables is 0. Then the first constraint, okay, since the sign of the first constraint, second constraint and the third constraints are less than or equal to, therefore we need to add select variables to each constraint. Okay, the first constraint, the basic variable in the first constraint is S1. Okay, we have x1 plus 2x2 plus 1x3 plus s1 equals to 430. Okay, row 1. Now for row 2, 3x1 plus 0x2. 3x1 plus 0x2 plus 2x3 plus s2 equals to 460. And for row 3, we have x1 plus 4x2, x1 plus 4x2 plus 0x3 plus s3 equals to 420. Okay, write the basic variable for row 2 and row 3. Now, after we modify the model, we need to consider D1, D2, and D3 in row 1, row 2, and row 3. The right-hand side of row 1 becomes 430 plus D1. So 430 plus D1 and no D2 and D3. For row 2, we have 460 plus D2. 460 plus D2. Okay, the coefficient of D2 in row 2 is 1 and coefficient for D1 and D3 is 0. And for row 3, we have 420 plus D3. So 0 here, 0 and 1. So we have 0, 0, 0. As we can see here, the two shaded areas are identical. This part and this part. Hence, after a few of simplex iterations with same row operations, ERO, as in the original model, the columns in the two highlighted area will also be identical in the optimal tableaus, as shown below. So this is the optimal tableau. Okay, optimal tableau of the original problem. Okay, but here we have new columns on the right hand side of the RHS. Because in the initial tableau, these two areas have the same coefficients, therefore they also will have the same coefficient in the optimal tableau. Okay, we need to fill in these columns and the element on this column same as element in columns like variables. Okay, we have 1, 2, 0, 1 over 2, negative 1 over 4, 0, 0, 1 over 2, 0, negative 2, 1 and 1. Okay, and we need to fill in the column of BV. Okay, BV for the first constraint is x2. Okay, because this variable only exists in row 1. So x2 here. For row 2, the basic variable is x3. And basic variable in row 3 is S3. This new optimum tableau provides the following optimal solution. Okay, before this, we know that the value of Z is equal to 1350. But now we need to consider D1, D2, and D3 in every right hand side. Okay, therefore, row 0, Z is equal to 1550 plus D1 plus 2D2 plus 0 D3. And for row 1, the value of x2 now is 100 plus 1 over 2 D1 minus 1 over 4 D2 plus 0 D3. And now x3 is equals to 230 plus 0 D1 plus 1 over 2 D2 plus 0 D3. And for S3, the value of this variable is 20 minus 2D1 plus D2 plus D3. And this optimal solution can be used to determine the dual prices and the feasibility ranges. Dual prices can be determined from the new row 0, where here we can see Z is equal to 1350 plus D1 plus 2D2 plus 0D3. Okay, the coefficient of DI represent the dual price for the ith constraint. Okay, as we can see in this equation, a unit change in operation A capacity where we give the value of D1 equals to 1, okay, will change Z by 1 ringgit. For example, okay, we know that the availability operating time in operation A is 430 minutes. Okay, in the original problem. But now, Toyko increased the operating time in operation A to 431 minutes. Okay, we know that here D1 is 1 minute. Okay, it increased 1 minute in operation A. And the operating time for operation B and C remain unchanged. Okay, means D2 and D3 equals to 0. Okay, now what happened to Z value? Okay, Z will becomes 1350 plus 1 times D1 is 1. Okay, plus 0 because D2 and D3 are 0. Therefore, Z becomes 1351. Okay, we can see that the value of Z increased by 1 ringgit. Means 1 minute change in operating time of operation A will change the Z value by 1 ringgit. Okay, now for operation B, a unit change in operation B capacity where we increase the operating time of operation B by 1 minute, change Z by 2 ringgit. Okay, because the coefficient of D2 is 2. Okay, meaning that a unit increase in the number of operation B will increase the optimal Z value by 2 ringgit. And now for operation C, a unit change in this operation capacity change Z by 0 ringgit. This shows that the optimal Z value will remain unchanged even if the right hand side of this constraint is changed. By definition, the corresponding dual prices for operation A is RM1, operation B is RM2, and the dual price for operation C is 0 ringgit. Okay, now let's move to feasibility range. The current solution remains feasible if all the basic variables remain non-negative, means that all right-hand side are greater than or equal to 0. Okay, we refer to the modified optimal tableau. Okay. In row 1, we know that the value of x2 is 100 plus 1 over 2 d1 minus 1 over 4 d2. And we need to make sure that the value of x2 is non-negative. Therefore, we set the value of x2 is greater than or equals to 0. Same to row 2 and row 3. We need to make sure the value of x3 where it is equal to 230 plus 1 over 2d2 is greater than or equals to 0. And S3 from the modified optimal tableau, the value of S3 is equal to 20 minus 2D1 plus D2 plus D3. We need to make sure the value of this variable is also non-negative, regardless the objective of the problem. Means that if the problem is to maximize Z, the feasibility condition of the problem is greater than or equals to 0. Means the value of each basic variables is non-negative. Okay, simultaneous changes D1, D2, and D3 that satisfy these inequalities will keep the solution feasible. Means all right-hand side are non-negative. The new optimum solution can be found by substituting out the values of D1, D2, and D3. Now, let's discuss example 4.3. Okay, refer to the Toyko original model. Okay, to illustrate the use of these conditions, where feasibility condition is all right-hand side are non-negative, suppose that the manufacturing time available for operation A, B, and C are 400, 448, and 430 minutes respectively. Then the right-hand side changes are D1. Okay, now the new operating time in operation A is 400. Before this, Toyko allocate the operating time for this operation is 430. So, D1 is 400 minus 430 is negative 30. Means Toyko reduced the operating time of operation A by 30 minutes. D2 is equal to 448 minus 460. Okay, we get negative 12. And D3 is 430 minus 420. We get 10. Okay, now we substitute D1, D2, and D3 into the feasibility condition of the Toyko original problem. Okay, we know that from the modified optimal tableau, X2 is equal to 100 plus 1 over 2 D1 minus 1 over 4 D2 plus 0 D3. Okay, now we substitute D1 into this equation. D1 is negative 30 and D2 is negative 12. And we calculate, we get 88. This is a positive number. Means X2 is equal to 88. And still, the current solution remains feasible. Okay, now, what is the new value of X3? From the feasibility condition, X3 is 230 plus 1 over 2 times D2. Okay, now we substitute D2 into this equation. 230 plus 1 over 2 times negative 12. So we get 224. Okay, this is a positive value. Okay, the new value of X3 is 224. Okay, means the current solution still feasible. And for S3 is equal to 20 minus 2D1 plus D2 plus D3. Okay, we substitute D1, D2 and D3 into this equation. We get 20 minus 2 times negative 30 plus negative 12 plus 10. We get equals to 78. Okay, the value of S3 now is 78. Okay, also greater than 0. Okay. Feasible means when all the value of basic variables are non-negative, therefore the current solution remains feasible. Means that X2, X3 and S3 remains as optimal basic variables. Okay, what is the value of X2, X3 and S3? From this calculation, we can see that the value of X2 is no longer 100. The new value of X2 is 88. X3 changed from 230 to 224 and S3 increased from 20 to 78. This is a new value of X2, X3 and S3. And X1 remain equals to 0 because X1 is NBV. Now, what is the value of Z? Okay, we can calculate Z by using the objective function. Okay, we know that the objective function of this problem is 3x1 plus 2x2 plus 5x3. We substitute the value of x1, x2 and x3 into the objective function and we get 1296. Okay, we also can use the dual prices to get the new Z value. Okay, from the modified optimal tableau, Z is equal to 1350 plus D1 plus 2D2 plus 0D3. Okay, we substitute D1, D2 and D3 into this equation. We get 1350 plus D1 is negative 30 plus 2 times negative 12 and plus 0 times 10. Okay, Z is equal to 1296. Okay, this is what we do when we have simultaneous changes to the right hand side of the constraint. Okay, these feasibility conditions can be used to find the feasibility ranges associated with changes the right hand side one at a time. Okay, we only change one right hand side at one time. What is the feasibility range for D1? Okay, D1, okay, we change the operating time for operation A and we remain the operating time in operation B and C. Means D2 and D3 are 0. Okay, from the feasibility condition, okay, we know that X2 is equal to 100 plus 1 over 2 D1 minus 1 over 4 D2 and D2 is 0. So, here we want to find the range of D1. So, we simplify this and we need to make sure that X2 is greater than or equals to 0. Okay, from here, we know that 1 over 2 D1 is greater than or equals to negative 100, and then D1 is greater than or equals to negative 200. And from the second constraint, the feasibility condition is 230 plus 1 over 2 D2. Okay, and we know that D2 in this case is 0. So we have X3 equals to 230, which is positive. Okay, and for S3, the feasibility condition for this variable is 20 minus 2 times D1 plus D2 plus D3. Okay, since D2 and D3 are 0, so we just consider D1. 20 minus 2 D1 is greater than or equals to 0. We rearrange this, we get D1 is less than or equals to 10. Now we have these two inequalities. Okay, to find the range for D1, we need to draw the number line. Okay, we have negative 200 and 10. Okay, we start from negative 200 and D1 is greater than or equal to negative 200, means the area of this inequality is on the right hand side of negative 200, and for D1 less than or equal to 10, we have, okay, the area is on the left side of 10. Okay, from this we can see that the range for D1 is between negative 200 and 10. Okay, so D1 is greater than or equals to negative 200 and less than or equals to 10. Okay, means that when D1 within this range, the current solution remains feasible. Okay, for example, Toiko decrease the operating time in operation A from 430 to 300. Okay, for example, from 430 to 300. Okay, we know that D1 is equal to 300 minus 430 is negative 130. Okay, since negative 130 still within this range, the current solution remains feasible. Means X2, X3 and S3 remain as optimal basic variable. If the value of D1 outside this range, the current solution is no longer feasible. Okay, therefore Toiko needs to calculate or find a new optimal solution for the problem. Okay, now let's move to D2. Okay, the feasibility range for D2 is when D1 and D3 are 0. From the feasibility condition, X2 is equal to 100 plus 1 over 2 D1 minus 1 over 4 D2 and greater than or equals to 0. Okay, here D1 is 0. Okay, we have 100 minus 1 over 4 D2 greater than or equals to 0. We simplify this, we get, okay, here we get negative D2 over 4 is greater than or equals to negative 100. Okay. And then D2 is less than or equals to 400. Okay. Now from X3 we have 230 plus 1 over 2 times D2 and greater than or equals to 0. Okay, we simplify this, we get D2 is greater than or equals to negative 230 times 2. So 460. Okay, D2 is greater than or equals to negative 460. And from S3, the equation is 20 minus 2D1 plus D2 plus D3 greater than or equals to 0. We substitute D1 and D3 as 0. So we get 20 plus D2 greater than or equals to 0. Therefore, D2 is greater than or equals to negative 20. So we have 3 inequalities. We need to find range for D2 by using the number line. Okay, draw the number line. We have here negative 460, negative 460, and then negative 20 and 400. Okay, we start with 400, negative 460. Okay, all value that greater than or equals to negative 460. See here on the right side of negative 460. Now, D2 also greater than or equals to negative 20 is here. Greater than. So also on the right side of the of negative 20. And D2 is less than 400 is here. Okay, from this shaded area, we can see that the range for D2 is between negative 20 and 400. Within this range, the current solution remains feasible. And the feasibility range for D3 is when D2 and D1 are 0. Okay. From the feasibility condition, X1 is 100 plus 1 over 2 D1 minus 1 over 4 D2 are greater than or equals to 0. Okay, we know for D3, D2 and D1 are 0. We get X2 equals to 100. This is a positive value. And now X3, 230 plus 1 over 2D2 is greater than or equals to 0. Also D2 is 0. Therefore, we get X3 is equal to 130. Okay, also greater than 0. And for S3, we have 20 minus 2D1 is 0 plus D2 also 0 plus D3 greater than or equals to 0. Okay, we rearrange. We get D3 is greater than or equals to negative 20. Okay, from here we know that the range for D3, so that for the current solution remain feasible, is greater than or equals to negative 20 but less than infinity. Okay, so this individual feasibility range. Now, we can summarize the dual prices and their feasibility range for the LP in table 4.2. Okay, we know that the dual price for operation A is 1 ringgit, operation B is 2 ringgit, and operation C is 0 ringgit. Feasibility range, okay, in operation A, okay, the range for D1 is between negative 200 and 10. D2 must between negative 20 and 400, and for D3 must greater than or equals to negative 20 and less than infinity. Okay, this is the individual feasibility range. Okay, so that the current solution remain feasible. Okay, the current operating time in operation A is 430. Okay, Toyko can reduce this operating time by 200. Okay, therefore, the minimum operating time in operation A is 430 minus 200 is 230. Okay, and Toyko can increase the operating time in operation A to 440 because the maximum D1 is 10. So 430 plus 10 is 440. Okay, for operation B, the current operating time is 460 minutes. Okay, to remain the current solution feasible, Toyko only can reduce the operating time by 20 minutes. Therefore, the minimum operating time in operation B is 460 minus 20 is equal to 440. And the maximum operating time is 460 plus 400 is 860 minutes. And for operation C, the current operating hours is 420 minutes. Okay, Toyko can reduce the operating hours to 400 and can increase until infinity and remains the current solution feasible. It is important to notice that the dual prices will remain applicable for any simultaneous changes that keep the solution feasible, even if the changes violate the individual range. Okay, this is the individual range. For example, the changes D1 equals to 30, D2 equals to negative 12, and D3 equals to 100. Okay, this is simultaneous changes. Because we can see that Toyko changed the operating hours in operation A, B, and C. These changes will keep the solution feasible even though D1 equals to 30, violates the feasibility range of D1. Okay, from this individual range, D1 must between negative 200 and 10 to remain the current solution feasible. However, okay, if the changes are made simultaneously, we cannot use this individual range because, okay, from this example, even though D1 is outside, D1 equals to 30, lies outside this feasibility range, the current solution remains feasible. Okay, because Okay, we use the feasibility condition when we made simultaneous changes. Okay, from the feasibility condition, we know that x2 equals to 100 plus 1 over 2 d1 minus 1 over 4 d2. Okay, d1 is 30 and d2 is negative 12. Okay, and we calculate this, we get 118, which is positive. Okay, means the current solutions remain feasible. Okay, for x3, we have 230 plus 1 over 2 d2, and d2 is negative 12. So we get x3 equals to 224, also a positive value. And for s3, 20 minus 2 d1 plus d2 plus d3. Substitute d1, d2 and d3 into this equation, we get s3 equals to 48, also a positive value. Okay, therefore, the dual prices will remain applicable and we can compute the new optimum objective value from the dual prices since the current solution remains feasible. Okay, from the dual price, we know that z equals to 1350 plus 1 d1, d1 is 30, plus 2 d2 is negative 12, plus 0 d3 is 100. And we get the value of z is 1356. These changes increase the z value by 30 ringgit and then reduce the z value by 24 ringgit. So 30 minus 24, we get 6. So z only increase 6 ringgit. Okay, from here we can conclude that feasibility range only can be used when we make a change at one time. If we have simultaneous changes, we cannot use this feasibility range. We only need to substitute di means d1, d2 and d3 into the feasibility condition, and when the conditions is satisfied, the current solution remains feasible and we can use the dual prices to calculate the z value. For your homework, please do exercise 4.2. And let's discuss example 4.4. In this example, Toiko changed the right hand side of the model such that D1 equals to 50, D2 is negative 20, and D3 is negative 20. Okay, because this is simultaneous changes, we substitute D1, D2, and D3 into the feasibility condition. Okay, where x2 is equal to 100 plus 1 over 2 D1, 50, minus 1 over 4 D2, negative 20. And we get x2 equals to 130. Okay, this is a positive value. Therefore, x2 can remain the current solution feasible. Okay, how about x3? Okay, from the feasibility condition, x3 is equal to 230 plus 1 over 2 times d2. d2 is negative 20. Okay, and we calculate, we get x3 equals to 220. Okay, also a positive value. Okay, we still can remain the current solution feasible. And for S3, we substitute D1, D2, and D3 into the feasibility condition. Okay, S3 is equal to 20 minus 2 times 50 plus negative 20 plus negative 20. And we get negative 120. This is less than 0. Okay, because of this, S3 less than 0, the current solution does not remain feasible. Means X2 or D or X3 or S3 is no longer basic variable. Okay, therefore, additional calculations will be needed to find the new optimal solution by using the dual simplex method. Okay, this will be discussed in the next video. That's all for now. Thank you.